So last time we discussed hydropower, and we said that we can extract power from water by converting, if you want, the gravitational potential energy into kinetic energy and pressure energy that can be used to drive, if you want, the turbine. We will convert it first to mechanical energy, and then the mechanical energy of rotation of the turbine shaft can be converted to electrical energy. So we'll do some problems to see how we can calculate the power that can be extracted through the turbine. Let us start with this first problem. So in general, the rule is really simple. It's the Bernoulli equation. We can use it in its simplified form in case losses are negligible, but in case we have, for example, long ducts and large distances, we need to include losses. And these losses, as we know, can be divided into minor and major losses. And we'll see in these problems how we can take them into account. So we'll start together with this first problem. The following figure shows a turbine that can extract 50 horsepower from the water flowing through it. So this is the power, and don't worry about units. I will give you in the exam all conversion needed. Okay, so horsepower is a unit for power. So it's in SI units, the unit for power is just watt. So if you want to calculate power extracted, power can be related to the head and turbine. So if you remember when we discussed Bernoulli equation, we said that it can be written in several forms. Okay, it depends on the unit of the term. So one of possibilities is to have all terms in unit of pressure. So we'll have pressure plus rho v square over 2 plus rho gz. So in case we are applying the simplified Bernoulli equation, no losses, where we neglect losses, we say that it's a constant. Okay? And then all of our terms will have unit of Pascal. Now, if we divide all terms by rho g, so the unit will be in meter, and we say that we are considering head of pressure, kinetic energy head, hydrostatic head, etc. Okay, so what we'll do together, we'll write the equation in head form, but we'll consider the most general case. So we can talk about uh, applying Bernoulli between points, for example, here between point 1 and 2. So the general equation will be P1 over rho g plus V1 square over 2g plus Z1. In case you have a pump in your system, the pump will add to the energy of your fluid. So you will put it from this side, and you put plus head of pump equals to, from the other side, you have at P2 over rho g plus V2 square over 2g plus Z2. And in this case, we can, if we have a turbine, we should add it from this side because the turbine will extract energy from the fluid. So we add plus turbine head. And of course, if we have losses, we need to add losses head. Okay. And the losses in general, you know, from fluids, they are divided into major losses and minor ones. Okay. Here, I will not go deep into details. If you want how to calculate friction factors, how to find minor losses, because this part is already covered in fluid, but just we need to know the formula used. So major losses are evaluated, will be due to friction effects, and they are given by the following formula: friction factor times the total length, if you want, of our ducting system over D times, which is the diameter if it's circular ducts. If not, if we have a cross section different than circular cross section, we can use the hydraulic diameter times V square over 2G. While for minor losses are expressed in the following formula. It's equal to sum of K, which are loss coefficients. So you know each type of fitting, valve, if you want, when you have a bend or entrance or exit, all of these will lead to losses. And we talk about minor losses in this case due to fittings and different types of valves or bands or etc. that can lead to losses. So we just say that it's sum of loss coefficients that are determined experimentally times V square over 2G. So in general, in this course, I will give you, and in case you need to account for minor losses, I will give you the summation of K, okay? And for major losses, I will give you the friction factor. You need just to know how to apply the rule in order to calculate the power extracted by your turbine. So if we apply this general formula for this example, first you have here a reservoir. So you have a large surface, okay? And it's exposed to atmosphere. So you have the atmospheric pressure is uh, reigning here at this level. So you can consider that P1 is equal to P atmospheric. And since the exit jet, yani, at the exit of turbine, your jet will exit to atmosphere. So you can say that P1 and P2 terms will cancel out because both are equal to atmospheric pressure. Now, concerning velocity, whenever we have a large free surface of a reservoir, so you have a large surface here, you can say that the velocity here is much larger than the velocity at the exit of the turbine duct. Because you know, from continuity, from conservation of, if you want, of mass, you can say that m dot at the surface of the reservoir, okay, is equal to m dot exiting the turbine. And m dot is mainly it's the mass flow rate, okay? It's equal to the density times the area times the velocity. So it's rho times A times V. And since if water is incompressible, rho is constant, so you can drop rho. And then larger your area, lower will be your velocity. So since area 1, which is the area of the reservoir, is much smaller than area 2, which is the area at the exit of your turbine, okay? Then you can consider that V1 will be, sorry, A1 much larger, okay? Because 1 is for the reservoir. So A1 is much larger than A2. So we can say that V1 is much smaller than V2. So we can neglect it in the Bernoulli expression. And whenever you have a very large surface, you can consider that V will tend to 0. So this term will cancel out. Okay? Now, since we don't have any pump in this system, HP is 0. So we are just left with Z1, which is which represents the elevation, if you want, of your water. Of course, you need to consider a certain reference. If you consider the reference here at the bottom of your reservoir, Z1 is just the elevation from the bottom. You can also take the level of the turbine to be the reference. It doesn't matter where you select your reference because what you care for is delta Z. So whatever the reference line position you consider, Z1 and Z2 will vary, but delta Z will remain the same. So for example, here I considered the level at exit of turbine to be the reference. That's why Z2 will be 0. And Z1 will represent the difference in height between the free surface and the level of exit of water from turbine. So, and here physically we know that what is happening actually is that we'll convert through the turbine, we'll convert this gravitational potential energy into kinetic energy. Okay, so يعني will convert until here into kinetic energy plus pressure energy, because here the pressure is different than P atmospheric. So you can have at this level transformation between these two stages. We have conversion between gravitational and pressure and kinetic energy. Now, when you go through the turbine, depending on the type of turbine, you know that some turbines will convert mainly, will extract kinetic energy and transform it into rotational mechanical energy. Other turbines will rely also on pressure. So if you have high pressure of your flow, you can extract energy from it. So depending on the type of turbine, you will know what will happen to pressure and velocity within the turbine. And then what we care for at the end is the amount of energy extracted. So we need to evaluate the head of turbine. Because once we evaluate the head of turbine, we can calculate the power. Here, they asked it in a different way. They gave us the power extracted by the turbine, and they want us to determine what will be the mass flow rate within the piping system. Okay, so first, what is the relation between power and turbine head? It's very simple. All you have to do is to look at units. You know that the unit for power, as we said, is what? And what is joule per second? And if you look at your terms, okay, you know, for example, that when we say, for example, concerning gravitational energy, if I say mgz, this is the energy, gravitational energy in joule, okay? So to have it in, to convert to what, I need to have it per unit time. So I can talk about m dot gz, okay? So if I have that in meter, if I multiply it by m dot g, I obtain a unit of joule per second, which is what? So all we have to do here is to say that the power extracted from the pump can be written as power equals the mass flow rate m dot times g times head of turbine. Okay, so if I have the power extracted and I want to determine what is the mass flow rate, I need to evaluate the turbine head. Okay, and I can evaluate it through my Bernoulli general Bernoulli equation. So first I will write the general equation. Then, as we said, I can start to do some simplifications, because P1, P2 equal to P atmospheric will cancel out. V1 is very small compared to V2. I can cancel it. I take Z2 at reference, so it's 0. And concerning the major losses, I can evaluate them because they gave me the friction factor F. So I just have to say that the head losses can be replaced by F times length of my ducting system. If I look in my figures, they gave me. If I look at my figures, they gave me the total lengths. If you want, I have 3 feet long ducting system, and I have the diameter also given. It's 1 feet. And I have the friction factor. So all I have to do is to just replace in the equation. Okay. They also told me, okay, that I have, if you want, as we said, we have everything. They gave me the formula of major losses. So I just have to plug in this formula. So now, if I, after my simplification, I have this. So I have, when I replace, I have everything function. And I just still need to determine, if you want, the expression, what is ht, and what is also my velocity v2. Okay. So when replacing back in my equation, in order to get ht, I need to relate, if you want, ht and velocity, because here I have two unknowns, which is the head and the turbine head and the velocity. In order to relate them, all I have to do is to go back to the expression of power. We said that power is m dot g times turbine head. So I can write that my turbine head is simply the power, which is given, okay, over m dot g. And m dot is function of my velocity, because m dot is the flow rate, mass flow rate through my duct system. So I can write it simply as, I can replace m dot by rho times cross-sectional area of my ducting system. And since I have the diameter of my ducting system, I can just say that AC is pi d square over 4. Times the velocity. So once I do this, I have now the turbine head expressed as a function of the velocity. So if I replace ht by its expression, okay, I can say that the only unknown in my Bernoulli equation is now v. Okay, so I get an equation where the only unknown is v. I can solve it, and then once I get the velocity, I can deduce the flow rate through my ducting system. Okay. Let us move to another problem. So here, water at 20 degrees is to be pumped through 2,000 feet of pipe from reservoir 1 to 2 at a rate of 3 feet cube per second, as shown in the figure. If the pipe is cast iron of diameter 6 inch and the pump is 75% efficient, what horsepower pump is needed? So here, if you want, this application is just the reverse of the application of extracting energy from dams. And when we produce electricity from water energy, we convert the gravitational potential energy into electrical energy, and we pass through different states. And first we convert from gravitational to pressure and kinetics, then to mechanical, then to electrical. Here, it's exactly the opposite. So here, you need to provide, your input is electrical. You provide electrical energy to your pump, and your pump will give, if you want, this electrical energy will lead to rotation, will be transformed into mechanical energy of rotation. In this case, if you want, for your pump, or depending on the type of pump, you have several types of pumps. They can work, you have some displacement positive pumps, where you can rely on alternative motion to create the variation in pressure. You can talk about rotary shafts, where you convert the rotational energy into increase in pressure, etc. So it depends on the type of pump. You can convert energy from one form to the other, but at the end, the purpose will be to give energy to your fluid. So you'll convert this electrical energy into an increase in energy of your fluid in pressure form. You increase the pressure of your fluid. So what will happen then after this, once you increase this pressure, you can then, after, convert this energy into gravitational energy by pumping water to high levels. So you can have, after, you can convert it to gravitational potential energy. So it's exactly, if you want, the opposite scheme of producing electricity from from storing water at high level. Here it's the opposite. If you have electrical energy and you want to store water at high elevations, you can use a pump. So here, in order to determine the horsepower needed, we need to consider, of course, the efficiency of the equipment that we have, plus, which is, each pump or each turbine also will be characterized by a certain efficiency. In the previous problem, for example, okay, they gave us the power that is extracted from the water. But actually, when you want to convert it to electricity, you will have some losses because of efficiency. So if they want us to determine what is the electrical work, the electrical power extracted, they should give us the efficiency of the turbine and the alternator system. You have an overall system to convert from, if you want, from turbine extracted energy to electrical energy. So you need to take, if you remember when we considered the description of the system, we said that we'll go through different stages and each stage will have a certain efficiency. So we can calculate like an overall efficiency to determine the electrical power extracted. So then you can say, if I have this overall efficiency, I can say that the electrical power extracted will be the power extracted from the water by my turbine times the efficiency of my turbine system, of course. Okay. So now here, as we said, we are working in the opposite way, and we need to determine what will be the value of the power supplied to the pump, electrical power to be supplied in order to perform this operation. So here, to do the analysis, we can try to select points at which we know more information. And here, for example, you can say, I want to apply Bernoulli between the inlet and the exit of the pump, but you don't have any information about pressure velocity in these 2 points. That's why you can say, let me start by relating the energy state at these two levels because I have information. So if this is point 1 and this is point 2, I have free surfaces here. So we said exposed to atmosphere. So whenever I have a free surface exposed to atmosphere, I can say that P1 is equal to P2 equal to P atmospheric. And since I have a very large reservoir, so I can, for both cases, I can say that V1 and V2 are really small, so they can be neglected. Okay. And now I am left with the hydrostatic heads. So I need to take a certain reference. You can take, for example, the reference here. If you take the reference at free surface 1, so Z1 is 0. And Z2 is plus 120. Just you need to pay attention for units, okay? So if you work in SI, you just have to take pressures in Pascal, V in meter per second, Z in meter, and your power in watt. Okay, and in English units, you can just you should know that the force in Newton, okay, in English units express in lb. So since pressure is in Newton per meter square, so in English units use lb per feet square. Okay. Now, if you want to simplify our equation, so when we write our equation, okay, so the general equation here is P1 over rho G plus V1 square over 2G plus Z1. Here, since we have a pump, so we have plus HP equals to uh, P2 over rho G plus V2 square over 2G plus Z2. And of course, we need to consider losses. And here they gave us the friction factor, so we can evaluate losses. So plus Z2. And we'll replace the losses had by a friction factor. So if they don't give you anything, if they don't talk about minor losses, they don't give the loss coefficient, the sum of K, you just consider that minor losses are negligible compared to major ones. So you have FL over D times, please pay attention here. You have V square that is used here is the average velocity in the duct system. So when we talk about V1 is the velocity at section 1. V2 is the velocity at section 2. But this term, the velocity in the major losses term, is the velocity within the duct. Okay? So you need to, you can solve here if you want. After, if they give you the flow rate circulating in your pumping system, you can say that this velocity is equal to the flow rate pumped over the cross-sectional area of the duct. And this is the case here because they gave us that the flow rate between reservoirs 1 and 2 is equal to 3 feet cube per second. So we have the value of Q, which is the volumetric flow rate. We divide it by the cross-sectional area of the duct. And since we have here, just we need to convert from inch to feet. So we divide, just have to divide by 12. And we say that the area is pi d square over 4. Okay, so now we can simplify a lot this expression. We said P1 equals P2 equal P atmospheric. V1 and V2 are negligible. Z1 is 0 because we considered the free surface one as reference. So we are left with HP equal to Z2 plus the major losses term. And here we can see the conversion of energy. So the pump will, the energy given by pump to the fluid will help us into gaining gravitational potential energy and will overcome the losses through the path of motion. Okay, so the pump is here to give us an additional energy that can help us into moving upward. You know that you cannot pump water up if you don't give energy to your fluid. Plus, you need not only to give it the just energy to go up, you need to overcome any friction also. Okay, so you need to give energy to store in gravitational form. Plus, you need to consider that I have some losses when I move upward, so I should overcome also these losses to be able to pump my water to the desired level. So now, after doing this, we just have to replace. So we have here delta Z, we have an elevation of 120 feet, and we have the friction factor is given. We calculated the velocity from the flow rate, so we can calculate the pump head. And once we calculate the pump head, okay, we should not forget to consider first to get the power, we need to multiply by m dot times G. And m dot is simply the density of our fluid times the volumetric flow rate, which are both given here. So you just have to replace and get them. So when I do m dot GH pump, I just calculate the power imparted by the pump to the fluid. So this is the power gained by water as it flows through my pump. But this is not the input power to my pump because I have a certain efficiency for my pump. My pump is 75% efficient. So this is the useful work that I can extract from my pump. But the input is larger because I have losses in my system. So since I have the efficiency, I need to divide the useful power by 75%. in order to find what is the electrical power that should be supplied. Okay, and here they just divided by 550 to convert to horsepower. Okay. In this problem, we want also to evaluate the power extracted by a turbine that is placed at 40 meters below the surface of a reservoir. So in this problem, knowing the flow rate extracted through the turbine is 0.004 meter cube per second, what is the value of power? Knowing that the head loss in total is 18.288 meters. So here, this loss can be from major or minor losses. We don't care because they already gave us the value. So all we have to do is to apply Bernoulli between state between point 1 and point 2. So when I do this, I can find the value of the turbine head, because if I write my equation, so again, P1, whenever you have a jet exiting to the atmosphere, so you can consider that P1 equals to P2 equals to P atmospheric. You have that the velocity at the exit of your turbine can be determined by doing Q over A, the volumetric flow rate over the area of your piping system, cross-sectional area. Okay, so now if we write our equation, as we said, P1 will cancel out, V1 also. We can consider this is a reference. So we have Z1 from the first side equals to, from the other side, we have Z2, but since we considered that the exit is at the reference, so Z2 is 0. And we need to account for head losses and turbine head. So we can say that the turbine head is just Z1, which is 40, minus HL, which is 18.288. So HT is 21.5 meters. And in order to get the value of power extracted from water, we just have to multiply this by m dot g. Okay, and again, this represents the useful, if you want, this is the input here of our turbine. So we can take from the water this power, but the useful power actually is the electrical one. And here, if you want to calculate the electrical power, they should give you the efficiency of your turbine. So you say that the turbine efficiency is equal to the power extracted, to the electrical power produced by my system over the extracted power from water. And P extracted from water is evaluated as, this is m dot g times H turbine. Okay. Any question on this? Okay. Now we'll do the analysis of a turbine to see how we can convert, how we can extract the energy from the fluid as it will go through the turbine. So a steam turbine generator unit is used to produce electricity as shown in the figure. Assume that the steam enters the turbine with a velocity of 30 meters per second at an enthalpy H1 of 3,348 kilojoule per kilogram. The steam leaves the turbine as a mixture of vapor and liquid, having a velocity of 60 meters per second and an enthalpy of 2,550 kilojoule per kilogram. the flow through the turbine is adiabatic, and changes in elevation are negligible. Determine the work output involved per unit mass of steam through your turbine. So here, if you want, we are just doing a small review about what we have seen in previous chapters. Whenever you have a system, يعني, where you have mass flow rate in and mass flow rate out, you can apply the energy equation. Then you need to consider the energy flux at inlet, energy flux at outlet, and possible work and heat rates exchange with the surrounding. So here, since I said that you have in a diabatic turbine, Q dot will cancel out, and your purpose here is to determine the work that can be extracted by your turbine from the fluid. So your equation will just be work extracted at turbine level is equal to the difference, if you want, in energy between outlet and inlet sections. Okay, so you just have to apply the general form, which is m dot total energy at state 2, which is H2 minus H2 plus V square over 2 plus GZ minus H1 minus V1 square over 2 minus GZ1. So here, this is the variation in energy of your flow between the inlet and the outlet. And since they gave you the enthalpy at outlet and at inlet, you can just replace. And they gave you also the velocities at sections 1 and 2. So here, in general, we used to neglect these terms, if you remember. In general, we said that in turbines, variation in potential and kinetic energy are negligible compared to variation in enthalpy. But in case they gave you velocities, you can evaluate these terms, but they will be much smaller than the variation of enthalpy of the fluid. So when you replace in this equation, you can just get W dot over M dot, which is the value of power per mass flow rate that can be extracted through your turbine. And here we can see that when we go through the turbine, the enthalpy will decrease a lot because the turbine will extract energy from the fluid. It will extract energy in pressure